Catherine told us about what we know, overall about the comets or a comet. Now, these comets, including this CG, most likely come from Kuiper belts, right? And Kuiper belt is about 40 AU away from us, plus minus whatever it is. And the next speaker, Dave Jewitt, who is a professor at UCLA, actually, who is an English.
Not anymore.
Yeah, okay. But that's what you sent it to me. So he's an English astronomer. That's what it says in his, bio.
I didn't say that, but it says that on the web somewhere.
Exactly. Yeah. So anyway, he's a UCLA professor at Planetary and Space Sciences department. And David is known, and actually not only known, but he discovered the first KBO object. So he is going to take us where Catherine left and to the origin of these kind of comets, how they have formed. Dave.
Okay, so is the volume okay? I have a quiet voice. Can you hear this well or not?
Yes.
Okay. And I have a bit of a cough. So here's the title of the talk, Kuiper belt to Comet. In deciding what to talk about, I looked at the instructions, and I wish to obey the instructions carefully delivered to me. And the instructions were like this. So first of all, the short course is designed to provide a foundation for everyone to understand your field. Limit your material to your discipline's 101 level. So that's a little bit open to interpretation, but 101 I think means, keep it simple. So I'm going to keep it simple. And I really like talks and lectures in general that start, in fact, too low instead of too high. If they start too high, you get lost. So I'm going to do that. And then the second really important instruction apparently is this one. Please wear solid colors, navy blues, grays, purples, dark greens. Okay. So those are the only instructions I have. Now the other thing is that I really like all Apple products. And I really like the big new iPad. And I really like handwriting on the iPad. So actually yesterday I just sat down and wrote some notes. So most of what I'll talk about will be stuff that I wrote down freeform yesterday. On my iPad. And we'll see how that goes. So here's a background. So we have three reservoirs of comets that we know about in the solar system. So we have the Kuiper belt, which is this ring essentially beyond the orbit of Neptune, starts at about 30 AU, goes out at least several thousands of astronomical units. We have, contains maybe 1 billion objects bigger than 1 kilometer. We have the Oort cloud, contains probably a few 100 billion comets in a spherical assemblage that is much larger. It goes out a large fraction of the way to the nearest stars, in fact. So characteristic radius of that thing is maybe 50,000 AU, something like that. So we cannot actually see the Oort cloud directly. We only see comets falling in from the Oort cloud. The objects in the Oort cloud are too faint for any technology we can imagine, except perhaps a spacecraft that would go out there and visit them. But that would be a mission that would take longer than our lifetimes. So I don't think we're going to see that. Unless we have main belt comets. So these are objects discovered in the last 10 years, which look like comets but have the orbits of asteroids. And a fraction of these, about 1/4 of these objects, appear to be sublimation driven in the sense that they're active at successive perihelia. So Catherine mentioned those briefly. We'll just talk about these sources briefly, but for the most part we're interested in the Kuiper belt because this is the major source of the kind of comet that we're likely to visit using a spacecraft, and that's the thrust of this workshop. So I have a schematic diagram that just is kind of background again. So we start with protoplanetary disk, and it produces comets in these different reservoirs. So the very distant reservoirs, the Oort cloud, the trans-Neptunian reservoirs, the Kuiper belt, and the main belt reservoir is the main asteroid belt. So this is 2 AUs from the sun, 50,000 AU and 30 AUs and beyond. And we know, because of decades of study, that the comets from the Oort cloud are ones that appear in our samples primarily as long period comets. And we know now that the Kuiper belt feeds a population of short period comets, in particular the Jupiter family comets. Their motions are strongly influenced by Jupiter. We know that these clouds formed at the beginning, so they're 4.6 billion years old. We know the transport time from Kuiper belt to the inner solar system is about 10 million years. And we know, and I'll mention this again in a moment, that once inside the orbit of Jupiter, the dynamical lifetime of the Jupiter family comets is very short. It's about 500,000 years, something like that. So they're fireworks on the way out. They're dying. They're falling to bits. So that's kind of the layout, the conceptual layout of things that I'll be talking about. And the acronyms, so astronomers like to classify things. Scientists in general like to classify things and give little acronyms to things. Don't worry about what they are. They're different subgroups of essentially the same object. So in recent years, we've figured out for the first time what are the likely relationships between these different things in the boxes.
Dave, can I ask you one question?
Yeah.
The Kuiper belt objects, 4.6
Yeah.
billion years, they stay there, and once they're scattered, then their lifetime is approximately 10 million years.
Yeah, so once so in the Kuiper belt, they're protected by various means from close interactions with Neptune.
Yeah.
Once something happens, so it could just be dynamical chaos that causes some to drift out. Once they approach Neptune, all hell breaks loose. Neptune can scatter them into Uranus or outwards, and so the giant planets take control. Then those objects are what we call centaurs. We just give them different names for some reason. They're centaurs, and they don't exist for long because of strong gravitational scattering events by the giant planets, massive giant planets. And so that's a 10 million year thing. And then in here, they're in the tiny inner space of the solar system. They're scattered by the terrestrial planets.
So yeah, once they come out 15 million years, or 10 million years, they're gone.
Once they're out, they're finished. Yeah. Okay, and then we don't have very nice pictures, but we have artistic representations. So here's the Oort cloud. You can't see the Oort cloud. It's dramatically optically thin. The optical depth is 10 to the minus 12 or something, so you couldn't see it even if you were outside the solar system looking in. But it's some roughly spherical assemblage. It previously was part of the inner solar system. Probably the comets in the Oort cloud were scattered out during the process of giant planet formation, and originally occupied a big disk, but the big disk has been isotropized by external perturbations from passing stars and helped by the tide, the galactic tide, which is this asymmetric pull on the Oort cloud from the outside. So Oort cloud is a very big structure, 100 billion things, and the Kuiper belt is comparatively small, starts at the orbit of Neptune, and 1 billion objects, and it's disky. And so it feeds comets which have a small inclination and a small eccentricity into the inner regions of the solar system. So we think, as Catherine said again, 67P probably is from here. Let me just give a little bit of a word about the active asteroids, because they're new and so a lot of people don't know about them. Here's distance from the sun, the semi-major axis. Here's the orbital eccentricity. So circular orbits at the bottom and basically parabolic orbit at the top here. These yellow dots are the asteroids. You can see Kirkwood gaps in the asteroid distribution. These blue things are what are classically labeled as comets. And the red things are objects that we've discovered in the last 10 years, literally, which are clearly in the asteroid belt, but which have the physical appearances of comets. So they're mass-losing asteroids. And a fraction of those are periodic, are known to be periodic. They repeat at perihelion, indicating there's some thermal control of the loss of mass. And the logical explanation there is that there's a volatile, water probably, that sublimates at perihelion. We haven't detected water in these objects. We haven't got a spectroscopic detection of water. But the reason is their mass loss rates are very small. So they're much less active than most of the things that we label as Jupiter family comets, for example. Anyway, they're there. And they look like that. So they are definitely not just boring point source asteroids. Apologies to anybody who finds boring point source asteroids interesting. They're ejecting material. They look like comets, hence the name, main belt comets. Sometimes we call them active asteroids. So they actually would be, I think, great targets for the kind of mission we're talking about, something with a lander that's going to sample material because they have asteroid-like orbits. So they're not very far away, and the eccentricities are very small. And so we know that we can reach the asteroid belt, and it's relatively easy to reach certain bodies in the asteroid belt. And so these would be great places to go. The negative is that the gas fluxes are very small compared to the typical Jupiter family comets, maybe 100 or 1,000 times smaller. So instead of a few hundred or a few thousand kilograms per second of water coming out, you would have maybe 1 kilogram per second of stuff coming out. Okay, but anyway, they exist. And people are, as we heard, talking about sending spacecraft there. That would be cool. Very briefly, Kuiper belt, the same kind of diagram, distance from the sun, orbital eccentricity, circular at the bottom, elliptical at the top. We discovered in the Kuiper belt that there's a highly non-random distribution of objects. So they don't fill up the diagram. They are preferentially located in certain regions. Neptune in this plot is here at 30 AUs from the sun and essentially 0 orbital eccentricity. We see, this was all completely a surprise, so none of this was predicted. We see a lot of bodies piled up in mean motion resonances with Neptune. And they're there because they're essentially protected from close interactions with Neptune by being in the resonance. So these guys are long-term stable. This one here is called Pluto. They're long-term stable, but at the edges of the resonances are chaotic zones. And so the chaotic zones at the edges of resonances are a possible source location for Jupiter family comets. So, these guys are stable, but the ones right there next to this on long time scales are dynamically unstable and can drift in to become giant planet crossing and then kicked in to become Jupiter family comets. So that's one possible source. And then this thing here, this big arc of scattered Kuiper belt objects, this consists of bodies which meet Neptune, only at perihelion. They come in close to the sun. Neptune may be there, maybe not. But on long time scales, they are successively kicked by Neptune, so they can diffuse up this diagram. They can also diffuse out and come in towards the inner regions of the solar system. So most people would say that this is the likely source subpopulation of the Kuiper belt, providing the Jupiter family comets. But we don't know, actually. It's likely, but we don't know, because it's hard to assess this population because on the average, they're quite far away from the sun. Hard to see these objects at all with the existing telescopes. And we cannot see any kilometer-sized thing in the Kuiper belt at all. So we have to do extrapolations from the population of larger bodies to the smaller ones. So it's very hard to make a direct comparison between the flux of Jupiter family comets coming in and the source region in the scattered component of the Kuiper belt far away. Okay, so I wanted to just do this in tutorial style. So Europeans are comfortable with that. Oral is looking happy, are comfortable with tutorial style. Americans don't know what that is. But what that means is Dave sits down on his iPad and writes some notes and then talks about it. So just as a reminder, since we want to get everybody on the same page, let's talk about thermal diffusivity. If you have a solid body with some radius r, the heat content in that body is just the mass times specific heat times the temperature. So it's density, radius cubed, specific heat, and temperature. The rate of loss of heat basically is proportional to the temperature gradient across the radius. So if we say the edge is 0 Kelvin and the center is hot at some temperature T, the flux of heat conducted outwards is the surface area, 4 pi r squared, times the conductivity times the temperature gradient. And since we don't know what to do with the temperature gradient, let's just replace it by temperature divided by radius. And then let's estimate how long it takes conduction to carry heat out from a body by conduction. So that's just the total heat content divided by the rate of loss of heat So take these two equations, and you get this thing. The time scale for losing heat or gaining heat by conduction is the density, specific heat, and the conductivity multiplied by the radius squared. So that thing has a name. The inverse of that thing has a name. It's the thermal diffusivity. It's got those horrible units of square meters per second. But it's the only thing you need to know if you're thinking about conduction. If you care about conduction in some body and you know the size of the body, the physical parameter that you need to know is the thermal diffusivity, not the conductivity separately, the density separately, and so on. Okay, so that's a background iPad note. So for dielectric solids, like the cake that you just ate outside, or a piece of cheese, or a rock, or ice, the thermal diffusivity is roughly 1 watt per meter per Kelvin divided by the density divided by specific heat. It's about 10 to the minus 6 square meters per second. If you powder that material, you grind it up into little bits, you reduce the diffusivity potentially by a lot. And so a more plausible estimate for a comet, which we think is a very porous body, we know the densities are not very high, so they're porous inside, probably a better estimate of the diffusivity is 10 to the minus 8 square meters per second. What that means is very hard for heat to conduct through, because there are a lot of open spaces and not many contact points between the grains through which the vibrational motions can transmit. So we can do a couple of cool things immediately with our little estimate there for the cooling time. It's the radius squared divided by the diffusivity. Keep that in mind. So you can ask, what's the biggest body, what's this radius that can cool in the age of the solar system? So if you found something hot 4.5 billion years ago, shove 4.5 billion years into there, use some plausible diffusivity, 10 to the minus 8 square meters per second. If you do that, you find a characteristic radius of about 30 kilometers. So the first thing you know is the comets that we're interested in studying, things like 67P, are too small to retain primordial heat. So they're not like the Earth, which retains a lot of primordial heat. They're just too small to do that. It would all have leaked away by conduction in the time since formation. So the internal thermal structure is not primordially determined. It's determined by other things, like sunlight falling on the surface, maybe radioactivity releasing heat inside. The conduction time for a 1 kilometer radius comet, just for reference, is about kilometer squared over 10 to the minus 8, 10 to the 14 seconds. It's about 10 million years, something like that. So it's a short time. What about aluminum-26 heating? We know from the meteorites that that's an important early heat source. And we can represent that heat source by this function. So it's some initial power production rate multiplied by some exponential function of time, where this tau 26 is like 1 million years. So the aluminum decay time scale is almost 1 million years. The e-folding time is 1 million. So the argument, and I just put it in here for reference, I won't talk about it in detail. The argument basically is, if you form the comets at the beginning, you capture the heat that's produced in the beginning, and initially aluminum-26 is very powerful, and so you make the body very hot. The heat is retained in the body for the conduction time. So this region shows you basically some initial formation time, and here's the formation time plus the conduction time. So all of this heat is trapped. If you slide this up to the beginning, you trap a lot of heat. And that contradicts what we know about comets, because it causes the volatiles to be lost. So we have these measurements of compositions and isotopes in comets that indicate very volatile rich compositions with likely formation temperatures that are like 20 or 30 Kelvin, 25, 35 Kelvin, something like that. So if you form the comets immediately in the protoplanetary disk, as soon as the aluminum-26 is dumped in from some nearby supernova, they would already have either melted or lost a lot of their internal volatiles because of the internal radioactive heating, even at kilometer scales, even at a 1 kilometer sized body. And after all, if you look at the asteroids, lots of those are rocks which have melted because of this effect. So you have to defer formation of the comets to some number of half-lives after the origin of the solar system. So that, I said, suggests delayed formation. To me, it requires delayed formation. And what that means is the models that one reads about in the literature, including papers like this one, a famous title, Asteroids Are Born Big, by Mr. Morbidelli, don't, to me, seem to fit the data at all. If they formed, by some streaming instability, some collapse of the nebula, they would just form too fast and they would be self-heated. So these models don't take account of the volatile nature of comets, basically. They ignore the compositional evidence and rely on some dynamical jiggery-pokery, as they say. So I think that these models are not going to work. They don't work. And slow accumulation, so binary accumulation by the slow collisional building up process is much more likely. Is a question?
Say a little more about how we know or what we know about the 1126 abundance.
I would like to defer that so I can get through the rest of the talk, but we have experts here, including Ed Young, who will tell you about that in great detail. Because I see my time is already ticking away. All right, so I mentioned that thermal time is about 10 million years. It turns out the transport time from the Kuiper belt to the inner solar system is the same. And what that means is that for a kilometer-sized comet nucleus, the inside is permanently out of thermal equilibrium with its local environment. In other words, it remembers, at the core, it remembers the temperature it had 10 million years ago. And that's not the temperature it has now, because it's been scattered to a completely different distance from the sun. So the nucleus is always out of thermal equilibrium on the inside. Okay, and we're interested about that because the stability of the ices we'd like to measure is totally controlled by the internal thermal energy distribution. Inside the orbit of Jupiter, the lifetime is even shorter. It's only 500,000 years. And so there's no possibility that the inside of a Jupiter family comet is in thermal equilibrium with the surface. So it's entirely possible, in fact, it's guaranteed that the comets are colder on the inside than on the outside. And it turns out that it's quite reasonable to expect you could find Kuiper belt temperatures, which are like 40 Kelvin, 30 Kelvin, in the cores of comets that at the surface are as hot as the Earth. So there's a big temperature gradient going down. And that's the thing that we need to understand in order to meaningfully sample the interiors of comets. So actually, if you put a sinusoidal heat source on the surface of the Earth and then measure the temperature as you go down, it drives a damped wave. And the wavelength of that wave is just the square root of the diffusivity and the period of the wave. So if you're interested in comet nucleus rotation in 10 hours or something like that, you shove 10 hours in there and you calculate a characteristic thickness of a few centimeters. So the diurnal heat up and down is confined to a very, very narrow skin on the surface of the comet. Hot at the top, colder underneath usually, but sometimes reverses. If you consider the orbit period, say 10 years or so, and stick 10 years in there, then you get a longer time scale, but it only goes as the square root. So it goes from 2 centimeters up to 1.5 meters or something like that. So it's still, actually my height is basically the wavelength of the annual thermal wave driven into the body. If you take the entire dynamical lifetime of a comet, 500,000 years from numerical integrations of the motions of comets, and shove that in there, you get a scale length of a few hundred meters. And so even if you look at a pretty old comet, one that's about to be ejected or to hit the sun or hit a planet, that pretty old comet is still going to retain cold ice deep down. The bad thing is that will be too deep for us to go with a spacecraft. That's all right. That might be all right, but that's not. So what you'd like to do is pick a comet that's not been in the inner solar system for very long, so that this heat has not had a chance to diffuse very deep down. The problem is that the motions of comets are chaotic. And so we don't know where the comet was even a few thousand years ago or earlier. We just can't tell because of the strong scattering by planets that we cannot integrate backwards for any individual object. Okay, I will just summarize this very briefly by saying this. I won't talk about that to save time, but sublimation is very rapid. So near the sun, the sublimation rate is about 5⁻⁴ kilograms per square meter per second. So 1 square meter loses about 0.5 gram per second through sublimation from this energy balance equation. And what that means is the surface, if you exposed ice, pure ice, to the sun it would sublimate down at this rate of roughly a micron a second, something like that. So it's really a very fast rate. And it's interesting to compare that with things that you might know, or I know. So my daughter, for example, grew at the rate of 10 to the minus 8 meters per second when she was a few years old. I told her that, and she looked at me like, why are you telling me that? This is also the rate at which trees grow. It's 100 angstroms per second. It's really fast, but sublimation is 100 times faster, 10 to the minus 6. So sublimation, unless something stops it, is capable of moving all the way from the surface of a comet to the core in a very short time scale. So 1,000 meters divided by 10 to the minus 6 per second is 10 to the 9 seconds. It's 30 years, say 100 years. It's very, very short. And so we have physical lifetimes of comets, which are very short. They're also very uncertain. We actually don't know what they are, because we don't know the fundamental process that in the end destroys a comet. But it's very short, even compared to this dynamical lifetime of 500,000 years that's been estimated from numerical integrations. So that's really interesting. That means the comets that we see really either have not been there very long, maybe just a few thousand years, or a few tens of thousands of years if you push it somehow, or they represent the active phase of some bodies that somehow shut down and manage to look like asteroids most of the time and then turn on later on. So there's the possibility, although not much evidence, for a population of dormant comets that we classify as asteroids, but which in fact are volatile bodies that sometimes burst into life. And so that would extend their long-term lifetime. Yeah.
So as you just said, the core of the comet
Yeah.
is much colder.
Right.
So does the added, the heat that you need to raise that temperature significantly increase its lifetime?
It does, and this is just a crude estimate. But when you do the detailed calculation for the total loss rate, you still get very short time scales, like 10 times longer or something. The actual situation is much more complicated because of second-order effects like mantling on the surface. So you have refractories pile up on the surface. They inhibit sublimation and so on. You had a question?
No, I answered it.
Okay, good. All right, so then let's speed into the last part. So this is just a quick summary, just again for background. The whole thing is for background. We have a range of time scales. So we have the residence time in the Kuiper belt, 4.5 billion years, a long time. We have the journey to the orbit of Jupiter. It's a 10 million year journey. There's a big scatter on that too, but the median is like 10 million years, which is also the conduction time for a kilometer-sized body. We have the aluminum-26 time scale. It's a million years for the e-folding time of aluminum-26. That influences how much heat can be trapped in the beginning in a growing cometary body, and tells us that delayed formation is I think, required to account for the presence of volatiles in comets. We have this dynamical lifetime once they're inside the orbit of Jupiter, determined by hitting a planet or being thrown into the sun, typically. And then we have this very uncertain physical lifetime over here, determined by some process, which could just be volatile loss, or my personal favorite is rotational instability, that a sublimating comet torques itself, spins itself up, and blows itself to bits rotationally when it spins too fast. So I think that's something that hasn't been discussed too much, but is a very likely source of the destruction of comets on a very short time scale. So there's a bunch of questions which we can discuss. I'll come back to that in the end if you like. I wanted to talk about amorphous ice because I think that's very important in the context of this meeting. So, there's amorphous ice and crystalline ice. If you have, so the ice in the fridge is crystalline ice. So the molecules are arranged in a regular lattice shape. If you drop water molecules onto a very cold surface, when they hit the surface, they just freeze in place because they don't have enough residual energy to bounce around on the surface. They just freeze, and you have a big pile of molecules with no particular long-term structural order. So that's called amorphous ice. If you heat amorphous ice up, then eventually you reach a point where the thermal vibrations of the molecules on the surface are able to cause the molecules to migrate, to skitter over the surface, and they fall into local energy minima, and they give out that energy. So it's an exothermic process, releases energy in going from amorphous to crystalline ice. So the very cold, low-pressure environment in the early solar system is ideal for the formation of amorphous ice, not ideal for the formation of crystalline ice. And so there's a lot of reason to think that the ice in comets in the beginning might have been amorphous ice. Now, this transition from amorphous to crystalline is a very strong function of temperature. So here's it's an exponential. This EA over K is 5370 Kelvin. So you can plug numbers in there, and you get this curve. What you find is in your fridge, which is probably about 265 Kelvin or something like that over here, the crystallization time is about 10 to the minus 12 seconds. So if you put amorphous ice in your fridge, it's crystalline within 10 to the minus 12 seconds, which is why you can be sure there's no amorphous ice in your fridge. As you come down to lower temperatures, you find that by the time you've reached 77 Kelvin, the crystallization time is equal to the age of the solar system. It's just amazing. It's really, really long. So if you have ice that's been kept at a temperature less than 77 Kelvin and it was formed amorphous, it would still be amorphous. Okay? The significant thing is that the Kuiper belt is entirely less than 77 Kelvin, the whole place. The radiation temperature is 40 Kelvin or 30 Kelvin, not 77. So ice in the Kuiper belt, if it were formed amorphous in the first place, should still be amorphous. And that means the comets should be amorphous as well on the interior. The question is, are they? Is that true? Oh, here's a nice little picture. Okay, so here's the idea that tells you about the release of energy from the crystallization event. So he's crystallizing the ice here. The energy released from this mousetrap here spins over and triggers these mousetraps here. So you get the idea. You can precipitate a crystallization, good face, you can precipitate a crystallization runaway, where the energy released in one portion of the ice goes on to trigger the crystallization to heat it up in the portion of ice next door. And so you have an explosive runaway of crystallization. I'm glad that he did that and not me. Okay, so you get the idea. You can release all of this energy that's built up by forming the ice at very low temperatures, and you release the energy when it crystallizes into the...
This is not allowed. There's no...
It's a safety hazard. I think you should do it all the same. So the energy that's released is about 100,000 joules per kilogram. This is substantial energy. Remember, the heat capacity of ice is like 1,000. And so this is enough to increase the temperature by 100 degrees if you have a perfect transfer to some parcel of ice next door. So what's the evidence? Well, we see comets in the solar system at distances which are perihelion distances which are too large for crystalline water ice to sublimate. So at 12 AU, the temperature is not big enough to sublimate crystalline ice in any measurable way. But this temperature, radiation temperature, is big enough to cause crystallization on a timescale comparable to the orbit period, the Keplerian time. And so crystallization is a plausible source of activity in comets that are outside the terrestrial planet region. So that's consistent with the existence of amorphous ice. I just plotted the same, these are centaurs, so bodies between the Kuiper belt and the short period population. These blue dots are active centaurs, and you can see that they kind of go out. Here's the orbit of Saturn right here. They go out to about the orbit of Saturn, a little bit beyond, maybe 12 AU, and then we don't see any of them out there. That's because it's too cold out there even for amorphous ice to crystallize. So I think the evidence from the distant comets is consistent with the presence of amorphous ice, but there's no proof. A cool thing that has been reported, but which needs to be explored in much more detail, is the ability of amorphous ice to trap gas. So this gentleman, who also recently died, Akiva Bar-Nun, has done lots of experiments with cold ice, amorphous ice, and looked at the mass of material that you can pack into the nooks and crannies of the amorphous ice. It's this big, hairy structure with lots of holes and spaces. You can absorb lots of other gases into those spaces. And so his claim is that at 30 Kelvin, for example, you can trap as much other stuff in the ice as you have ice. So you could have a sample of 1 gram of ice and pack into that 1 gram another gram, or even more, of other stuff, just by absorbing it. When you go to higher temperatures, the trapping decreases dramatically. When you crystallize the ice, the molecules of water rearrange, and all those spaces close up, and the trapped species are ejected. So you have a burst of gas, a pulse of gas that comes out upon crystallization, and you have this heat release. It's exothermic as well. And so those are the recipes for an explosion. And we see many explosions on comets, they're outbursts. What we don't want is to get a sample from a comet that's really cold bring it back in a spacecraft, heat it up, and have the spacecraft explode. So we need to think about the possibility of trapping super volatiles in a chamber in a spacecraft if we can actually get a very low temperature sample. Okay, so questions about amorphous ice. There are many. Is it actually abundant in comets? You know, is the dominant form of ice in comets in the Kuiper belt amorphous? If it is, how deep do you have to go? Depends on the detailed temperature profile, which depends on the diffusivity and the evolutionary history, the dynamical history of the body, which is in general not knowable. Does the amorphous ice drive the activity in some sense? Is it responsible for deep activity not really related closely to the surface that pushes out material? If the comets are amorphous, then their precursors, these bodies being scattered by the giant planets, presumably are amorphous too, and so are the Kuiper belt objects. But the puzzle is when we take a spectrum of a Kuiper belt object, it doesn't show amorphous, it shows crystalline ice. So there's a bunch of questions to consider as time goes on. And the dynamical questions are like this. You know, where are the Jupiter family comets from exactly? So we're pretty sure they're not from the Oort cloud. But where in the Kuiper belt does the source lie? People would say it's the scattered Kuiper belt objects. But we're not sure because of counting problems with those bodies. When and where did these guys form? So you may know there's a whole history of hairy models of the dynamical evolution of the solar system, most of which are untested and untestable. They don't make firm predictions. But they allow the Jupiter family comets to be formed much closer to the sun and then scattered out to their current locations in the Kuiper belt. Did that really happen? Where did they form? We don't know. What is the relation between the volatiles in the main belt comets at 2 and 3 AU and the volatiles in comets in the Kuiper belt, 30, 40, 50 AU? We don't know. Presumably they're not the same. Formation conditions would be likely quite different for the main belt comets. And what exactly is it that limits the physical lifetimes of comets? Is it just the loss of volatiles? Is the active phase just a transient phase in comets, which really live for a much longer time and only outgas for a fraction of the time? Or do they decay physically? Do they rotationally disrupt or disintegrate for some other reason? So those are a few things to talk about in the next few days. I'll stop there 1 minute late.